Today, as advertised, we're going to talk about actual math stuff. And we're going to begin with the definite integral. And we're going to think about the definite integral not as an introducing of the concept, but as a concept that we know a little bit about already. So we just want to summarize the little bit about that we know about the definite integral already, and then talk about how we want to think about the definite integral. So let's write down a definite integral. We know that one of the questions that we ask in math, in calculus, one of the questions, big questions in calculus, is to ask the question, what is the area under a curve and above an interval? So what is the area under the curve and above the interval? The curve is just the graph of the function y equals f of x. And the interval is all the x values that we're plugging in to the function. I'm going to use interval notation. So I'm going to put a comma b in brackets. This might be a new notation for some of us, but this is interval notation. The a is where the interval starts, b is where the interval ends. Square brackets indicate that a and b are included in the interval. So this interval notation is for all the values of x that are less than or equal to b and greater than or equal to a. Square brackets give us the or equal to part. If I had used parentheses, then the value contained by the parentheses would be not included. We know that the derivative tells us the slope of the tangent line, and that the integral is going to tell us the area under the curve and above the interval on the x-axis. A lot of times we just shorten this to say area under the curve because we're in single variable calculus. And we don't really think about switching over to multivariable calculus. But I want you to think of both the top and the bottom, under the curve and above the interval. There's the top, the curve, the bottom is the interval. And then just multiply by -1 if the function is underneath the x-axis. But the top is the curve, the bottom is the interval. And we have math symbols for this. We can write this as the definite integral from a to b of f of x dx. That's the definite integral of f of x dx from a to b. A lot of times I'm just going to read it in the order that it gets written, even though it comes out a little bit weird. So we say the definite integral from a to b of f of x dx. That would be the words that go along with this symbol. Remember how we construct the definite integral, the way that the thinking goes. What we're doing is we're assuming that the function f of x is constant for some small changes in x. Let's think about why this is. What we're trying to calculate is an area. An area is length times width. Now that you're in calculus, the only area that you need is length times width. All that other area stuff, that's just shortcuts to get through, to apply area is equal to length times width. All we need is length times width. Triangle comes from length times width. Circle comes from length times width. Parallelogram, that's cheating. That's just a rectangle. That is length times width. You have to decide what the length is. The problem is we want to do a multiplication, but one of our factors is not constant. If the function is constant, we get to multiply. If I've got a height of 3 and a length of 5, area is 15. I just take that height of 3 and multiply it by the width. But this length, this f of x right here, it's like, oh, I'm not gonna be constant. So we can't just do multiplication. Because we're like, oh, what's the height? And then we calculate, oh, the height's f at a. Great, and as soon as we move off of a, the function's like, oh, I'm changing my values. And you're like, oh, you jerk. And it's like, oh, ha, 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 ha. And it's just like changing. So we don't get to use multiplication. So the assumption works by saying, all right, calm down, function. We're going to assume that you're constant for some small change in x, because if we make you constant just for a little while, we get to use multiplication. And we just use height times the width. Height times the width. And then we just do that a bunch of times. So the assumption comes from assuming that the function is constant for small changes in the interval. The way the calculation works is we assume that the function is constant for small changes in x. Our strategy is to assume that the function is constant for small changes in x so that we can use multiplication to calculate area. And we just have to write area is equal to length times width. So the strategy is we assume that the function is constant for some small change in x. And we're going to be making a bunch of rectangles. So I'm going to index xi. We're assigning a height to the function or a length to the function and say it's going to be this for some small change in x. Because if we look close enough, the function does look flat. If we zoom in close enough to the function, it will look flat. Just like we're standing on a big spheroid, but we're zoomed in so far, we look around and it looks flat. If you haven't been to the Midwest, it looks flat and it's creepy how flat it is. Like in the Bay Area, you look around and it's like there's like mountains. So like there's only so much flat. But you go out to the Midwest and it's flat as far as the eye can see it. I got off the plane in Chicago. I'm like, oh, did we land in a Euclidean plane? Is this Euclidean now? Because it looks like it goes on forever. What are we talking about? Oh, yes. So this seems like a pretty radical assumption to make if our function is changing this much from f at a down here to f at b up here. But if we look close enough, we're looking very close. If delta x is very small, the function isn't changing that much. So this is not that radical an assumption. Now that the function is flat on top, we can calculate area just by doing length times width. And we give the width delta x. So that f at xi times delta x is one calculation of length times width. And we do this for a bunch of rectangles. Let's say n rectangles, and then we just add up all the rectangles. So that symbol says add up all of these n rectangle areas. So that's us adding up all the areas. And then we do the calculus thing. Calculus is just really about one thing. If someone asks you what calculus is about, calculus is the study of infinity. It's making rigorous the study of infinity. Before, infinity is this kind of weird concept that we don't understand. We know we don't understand it because as kids we're told to infinity and beyond. And you're like, oh, I thought astronauts had to have good math skills. So beyond infinity, it's just infinity. That's the concept. Now, it could be that Buzz Lightyear is just telling us a joke, but it seems that such a serious organization as Star Command shouldn't have like an inside joke, ha ha, for a slogan or a motto or whatever they call it. You know what I mean? I mean, you want us to take you seriously or not? What is this, an episode of Futurama? So here we are adding up all the areas. Now, what we know is that if we do this more often, if we use more rectangles, then our approximation will be closer to the actual area. And so we do the calculus thing. We'll just do an infinite number of rectangles. But we can't just plug in infinity because it's not like a number. So we say, well, let's take the limit as n goes to infinity. So that's just us saying use an infinite number of rectangles. More rectangles means a better approximation. Therefore, we do the calculus thing and use an infinite number of rectangles. That's the calculus thing. This is a very important thing to notice. Not just for the process, but for what we actually accomplish here. When we write this Riemann sum, this is where we get to have this crossover to the definite integral. But what we have on the left, before we apply the limit as n goes to infinity, is a discrete sum. It's countable things. It's n little boxes of length times width. But what's going on the other side is that this function is changing continuously. there is no next real number. Over here on the discrete side, there is the next box, the next index of I, the next number. But over here on the right, f of x is continuously changing, and there's no next real number. You can't pick a real number and say which one is next. The way you can say, if we've got the third box, the next one is the fourth box. If you've got the fifth box, the next one is the sixth box. If you've got the ith box, the next one is the I plus 1 box. It's a discrete sum that we have over here. And we're saying that if we do this an infinite number of times, it'll give us this continuous sum over here on the right. Now, in case you're concerned that I've been standing in the classroom and pointing at the screen instead of pointing at the paper where it will show up, I assure you, I did this when I was working from home too. I would make some kind of motion that I knew was not on camera, but only like after class when I was like, oh, people would not know what I was talking about because I wasn't pointing to it down here. I was pointing to it up here. And no one can see me pointing. Any questions? The important part here is the thinking, because if we get the thinking going about this, then we don't just solve one problem where we can find the area under the curve. That's a dubious suggestion at best. But if we look at the structure of what's going on, we can view this as a method. We did this problem to find area is equal to length times width. But all that's going on here is multiplication, where one of the factors is variable. Think about all the other things that we calculate with multiplication. Area is equal to length times width. That's a good one, so we could visualize what's going on up here. We can make rectangles. But distance is equal to rate times time. There's another multiplication. If the rate is constant for the entire time, then we get to multiply, lucky us. If the rate is variable, then we have to integrate the rate with respect to the time. Anywhere we have multiplication, where one of the factors is variable, is an integration problem. Volume is cross-sectional area multiplied by height. That's fine if the cross-sectional area is constant, like in a rectangular solid, it's length times width times height. Length times width, the cross-sectional area of the rectangle, multiplied by the height. The volume of a cylinder is pi r squared times h. Pi r squared is the area of a circle, and then we just multiply by the height. We get to use those formulas because the cross-sectional area stays pi r squared the whole time. We get to use the formulas because the area, length times width, stays constant the whole time. So we get to use multiplication. But what if we're looking at something like a piano leg that spent some time on the lathe and is circular in all its cross sections, but is not the same area? Well, we're back into the same calculation that we made here, the same assumption, and it works out the same way. Instead of length times width, we'll do pi r squared, that's the cross-sectional area, multiplied by the height, delta x. Because even though this piano leg has been on a lathe and it has different radii, it's always a circle, and we can count on that. The big limitation that we face is that we're in single variable calculus. So we decided to make our lives super difficult by saying, you only get to use one variable, really two. Y is a function of x in most in most of our calculations. So we really only get to use two, y and x. So I guess we're going to start with that, but life becomes easier if we get to use more variables. It becomes easier to set up problems. The calculations become a little bit messier. But this is what's at the core of our assumptions for integration. Then, of course, the real big deal that we have from all of this is the fundamental theorem of calculus. So that is actually revealing something about a connection between this area business and those derivatives. Oh, we've only had calc 1 and those derivatives, period. My tone didn't say what I was thinking. Like, oh, you're about to end the sentence. And my tone was like, oh, nope. I think there's another clause. And then I got to the end of the sentence. I was like, oh, no, I guess we're done. You know what I mean? It's like the question mark is an unfair punctuation. Because when you're reading, the question mark doesn't show up until the end. Oh, no, question mark is a fair punctuation. Because if you're reading the sentence, you see the question mark coming up, you say, oh, it's a question. You just have to up the end. So if I'm reading, are there any questions? But then I see that question mark coming up, and I go, oh, are there any questions? And then all of a sudden it's a question. What's unfair is the exclamation point. Because if I'm like, oh, reading no questions, and then the exclamation point is at the end, I'm like, oh, I should have been shouting this whole time. That's why the upside down one at the beginning, perfect. Because it's like, oh, hey, start shouting. And then when you get to the one at the end, it's like, oh, okay, you can stop now. You know what I mean? It's like in the little brackets, I, and then like the slash I for stop. So turn off the sound. It tells you at the beginning that you should be shouting. That's information that I need at the start of the reading. Question you can modify at the end. Anyway, what are we talking about? So the big conclusion in Calc 1 is the fundamental theorem of calculus. And we see the first part. So we get to the fundamental theorem of calculus. There are two parts to the fundamental theorem of calculus, but that's only because the fundamental theorem of calculus goes in both directions. Here's what we need for the fundamental theorem of calculus. We need a function that is continuous on a closed interval. So the fundamental theorem of calculus starts by saying, let f be a continuous function on a closed interval. Then the definite integral from a to b of f of x dx is capital F at b minus capital F at a, where capital F is an antiderivative of little f. That is, capital F prime at x is little f at x. This is one part of the fundamental theorem of calculus. This is something that we should just know. This is something when you're educated in calculus, if you are a modern major general and you're going to claim to be familiar with calculus, both differential and integral, then you have to be able to tell people the fundamental theorem of calculus, not just the weird symbol parts. Too often people are just like, oh, they go right for the weird symbol parts. Don't do that. Because then I'll just be like a jerk. Well, what if f is not continuous? What if f is undefinable? And then you have to go back and say, oh, no. F is continuous on the closed interval from a to b. And then the definite integral from a to b is f of x dx is capital F at b minus capital F at a Still not done because you introduce the capital F and you have to tell your reader what that is, where capital F is an antiderivative of little f. It's like if I asked you the Pythagorean theorem, don't say it out loud. But how many of you were thinking a squared plus b squared equals c squared? Don't answer me out loud. Because I'd make fun of you. I'm just kidding. I would not do that. But that requires a lot of stuff. That requires that A and B be the legs of a right triangle, and C is the hypotenuse of that triangle. We can't just interchange those around. So when you say a squared plus b squared equals c squared, you are assuming that your reader knows that C should be the hypotenuse of a right triangle, and that A and B are the legs of the right triangle. But we like that. We carry it around with us. A squared plus b squared equals c squared. If you want to make someone sound math and you're not sound smart, and you're not a very good writer, you have them recite some math formula. But then, since most people don't take calculus, it kind of ends in algebra. So like, oh, let's just have them say the quadratic formula. But then let's have them do it in a snooty way. Maybe even in a British accent, and they'll seem smart to American audience. X equals the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. What about that do you not understand? Right? Now you've established a lot of character in a really boring, sloppy way. Right? Because the answer is, what about that you don't understand? It's like, oh, I wasn't taught it properly in high school because you were taught the quadratic formula, and the quadratic formula is trash. If you use the quadratic formula to solve quadratic equations, you need to stop. You look like an amateur, and I will make fun of you for that. If you're like, oh, but what else is there? It's like knowing how parabolas. I'm just kidding. I wouldn't make fun of you for doing what you've been trained to do. It'd be the same as me making fun of students for chasing points. You're going to do that. You've been trained to do that. It'd be unfair of me to criticize students for doing the thing that we programmed them to do and chase points. Even though you know what the correct answer is. Michael, are you here in college just to get a degree? Or are you here in college to become educated? Right? You know what the school wants to hear. But it's really unfortunate that I don't think schools understand what the real question is. If money was no object and you could just buy a degree, would you? Don't answer. Because you think that I want to hear a certain thing. And so you just be lying to me, and that's okay. You can lie to me. We talked about that yesterday. I understand the dynamic. But think about it and be honest with yourself. If you could afford it, you just buy a degree. If money wasn't an object, not forever, it's like, well, hey, give me this pile of money that you have, and I'll give you a college degree. And then think about how much money that would be. And if you're telling yourself, I wouldn't do that, I'm here for an education, I would ask you to reevaluate, imagine just buying the degree. Put yourself in that situation, because right now your programming is telling you what the correct answer is supposed to be. And you're internalizing that message. But think about it real. Think about, you have like a get college degree free card. Won't do anything but like pay your rent or anything. You can't just trade it in. But if you turn this thing in, you'll get a degree from an Ivy League university. You'll get your bachelor's of science or bachelor of arts of science from Yale. Worry about doing the work. Actually imagine yourself in that scenario. Don't just say no because you think I think the answer is no. What are we talking about? Oh yeah, the fundamental theorem of calculus. The important thing to note here about the fundamental theorem of calculus is that we are establishing a relationship between this definite integral, which is just an area, and this calculation over here, which is based on the antiderivative. We're making an association between the definite integral and the antiderivative. And what we're saying here is that you can calculate a definite integral using the antiderivative. That's what we're claiming here. You can calculate a definite integral using the antiderivative. So tomorrow, when we write the second part of the fundamental theorem of calculus, it's just the other way. We can build an antiderivative using a definite integral. And the reason that this is good is that the definite integral represents area. And what's easier than area? Area is just length times width. That's why the fundamental theorem of calculus is so important. It takes this geometric idea and ties it to a rather complicated analytical idea, all in two parts of one super clean theorem. That's awesome. Every time I do the fundamental theorem of calculus, no one is impressed. I think I need more effects. I need Thanos to come in here and like snap and then like have stuff here or something. That's why I kind of start here, because all students that were in my Calc 1 class are like, oh, here he goes again with the stupid area thing. But you might not have heard this. Any questions? Okay, so yesterday I threatened you with chapter 12. Let's dial that back. There are homework assignments in chapter 5. Actually, there are homework assignments for the whole semester. Start with the homework assignments in chapter 5. I recommend, rather than doing the instructions where you read the textbook and then watch the video examples, just jump into the problems. See what you know in the problem. Scroll down, open the assignment, try some problems. Try the whole assignment. You can always skip problems and come back to it later. Just start doing work. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.